So hello everybody, and dynamic series once again. Today we will going to see the fundamental theorem for gradient. So let's start. Theorem for gradient. In some sense, it is the generalization of the previous theorem, which was the fundamental theorem for calculus. Okay, so let me just give you a brief revision about the fundamental theorem of calculus. So it was like this. So let's say we have a function f, okay, which is a one variable function, and the variable is x. So we'll take the derivative of that with respect to x. Okay, so this is the rate at which f is changing with respect to x. Integration over dx from the range a to b, let's say. So that will give actually the function, the value of function at b minus value of function at a, right? So this is valid for the one dimension. Okay, so that means we're gonna have this we're gonna have this for the one dimension. Okay, because this x is only there is only x present in the scalar field f, right? Let's say we have a three-dimensional space, okay, and some scalar field, let's say t, is distributed all over the space and time. Okay, so this is a scalar field, right, which is a function of x, y and z, and we have three variables this time, and we will write the same exact this equation in three-dimensional form. Okay, so first let me write it and then I'm going to prove it. Okay, so suppose that a particle move from point A, let's say, or say let move from a vector position vector A to some position vector B. So so what we know that when we take the gradient of that field dot product with the infinitesimal displacement vector, and this is the infinitesimal displacement vector dl, right, that will give, and of course it moves from position vector A to position vector B, that will actually give the field at point B, position vector B, minus t at point A, right? So this is it. This is the fundamental theorem for gradient. Now we are going to prove it. Okay, and one more thing, that you can see that this is the generalization of that equation, right? So instead of this derivative, we are taking the gradient, right? Instead of taking the infinitesimal displacement for only one variable, which is x, we are taking for the all the three variables, which is dl. And of course this instead of this point B, we are taking at a position vector B and A, right? Let's prove it. Okay, so let me first of all write this. The gradient of t is going to be del x t x cap plus del y t y cap del z t z cap, and obviously this and obviously this this is expanded in the Cartesian coordinate system. Okay, and dl is actually the infinitesimal displacement vector, which is dx x cap plus dy y cap plus dz z cap, right? And taking the dot product of all of them, that will give us del x t x cap del y t y cap plus del z t z cap, dot product with the dx x cap plus dy y cap plus dz z cap, right? The final equation will become like this: dx del y t dy plus del z t dz. Right. Now we can also write like this: dt by dx dx plus dt by dy dy plus dt by dz dz. Okay, which is equal to the gradient of t dot dl. And obviously this is what is this? So t is the variable of three functions x, y and z, right? We are changing the so what is this function? The first term represent the rate at which the t changes with respect to x, considering y and z as a constant, times the amount at which this x changes. Similarly for y and for z, and adding all these three will give us overall change of t. Okay, so finally we have proved it. That means this particular term will give dt. Okay, and once we take the integration all from let's say some position vector a to position vector b, so this will actually give us t at b minus t at a. So this is our proof. We have finally proved it. And yeah, you can also see that of course this when we look at this equation, so what we can see that this gradient of that field, okay, so I mean the gradient of this scalar field t will give a vector field, right? And taking the line integral of that vector field, okay, so this integration is actually the line integration of the vector field, this vector field. Okay, let me write it. Del t, let's say, is equal to a, and line integral of that vector field a is only depend upon a, okay, it's only depend upon a this t at the b and a. So that means if we are able to write a vector field in terms of its scalar, then the line integral will only depend upon the endpoints, okay, endpoints a and b. So it is path independent. Okay, so here we have our drawing. So instead of moving from a to b like this, or moving from a to b, let's say like this, in the both cases, because initial and final points are same, our integration, this integration is always be same. Okay, and from there we can also conclude that the closed integration of that particular term will actually give 0. Okay, because it is a closed integral, so we will just begin at the same begin at the point a and will return back to the same point b, and so both the points are same, so we're gonna have 0.